My name is David Blythe. I am a principal software developer at SAS. SAS is a leader in analytics. Our part of SAS does ad services, ad delivery services, which rely on user data that we store in Scylla. And my presentation is about how we kept our services running as we migrated from Cassandra, where we had that data, to Scylla with no downtime and with no inability to access data as we were making that migration.
You might have thought that the title of my presentation was a metaphor, but it's a thing. That's our front-end team working on, I think it's an Elasticsearch upgrade. Back-end team, we're exchanging databases. You know, it's not something you do very often, but when you do, and you've got a 24/7 service, you've still got to keep going. Okay, it is a metaphor. But by a show of hands, how many of you have responsibility for systems that have to be up 24/7? Right. And even though you've got these services that your customers consider critical to their business and have to be running all the time, you have to be exchanging the tires while it's going down the road. I think about this all the time. This is exactly what we do all the time. And the way we design our systems has to allow us to be able to do this. And so that's what my talk is going to be about today, is how we, oh, and by the way, what's this car doing in the background? I hope that's not our competition. Okay, upgrades are done for the week. And we're back now. Okay, good. So yes, I am David Blythe, and I work for SAS. Some people call it SAS, but they dropped the acronym a long time ago. I'm a back-end architect, developer, primarily writing in C++, although do a lot of scripting as well. For our product, which is a real-time ad decisioning platform, I take care of activation of data that we use for targeting, visitor data, which is what we keep in our NoSQL database, geodata, device data, application of business logic in how we make the decisions, the publication of the ad metadata to our servers, collection and processing of the serving data after the fact so we can provide reports of what's served and how many and all that, the automation of daily processing tasks for aggregating, doing the daily stuff that we have to do for our customers that doesn't need to be done in real time. A little bit about SAS itself. It's been a leader, I would say the leader in analytics since 1976. It's been around for quite a while. They started out providing statistical analysis tools. They still offer that sort of thing as a general purpose analytics tool set, but also provide specialized services for vertical markets such as healthcare, banking, and marketing. We're possibly the largest company you've never heard of if you don't know anything about SAS. We're the largest privately held software company in the world with revenues last year of $3.25 billion. And we have 14,000 employees worldwide, headquartered in Cary, North Carolina, which, in case my accent didn't give it away, I'm a native. Our part of SAS is called Customer Intelligence, which is one of those vertical markets that I mentioned. We provide services to digital marketers and web publishers for them to do analytics for A/B testing of content, to offer up product recommendations and tracking customer engagement. And we also provide, just for web publishers, we provide ad serving services so that we can control on behalf of them how ads are delivered into their web pages. It's multi-channel, so we can handle web, mobile, video, email. We engage a lot of complex business rules for targeting so that certain content only goes to certain people or in certain geographic areas. Things like limited exposure, so certain content is only displayed with a certain frequency. Or competitive exclusion, where the web publisher does not want competing advertisers to appear on the same page. And we deal with a wide variety of data, both from that the page itself may send us, but stuff that we might also look up through geo lookups, device data, visitor behavioral data and other visitor attributes that may have been fed to us by our client based on user registration. We serve many billions of decisions every month across all of our tenants, and our response times are generally very low. And we can have no downtime. So customer intelligence's use of NoSQL is really just a key value store. We're not currently doing any heavy analytics with NoSQL. We are simply wanting to get the serialized data that we've got for visitors into our system as quickly as possible when a visitor hits a website. So the key for us is the visitor ID. The data is some serialized data. It's rather arbitrary. It actually contains embedded collections and that sort of thing, but we serialize it for our purposes. We store it per visitor, so there are static attributes of the visitor, which might be things that they voluntarily gave when they registered for use of the site, such as gender, interests. And that's updated very infrequently by non-real-time servers. There's analytical data, which will, for certain of our customers, involve product recommendations, perhaps. That's also updated only periodically by non-real-time servers. And then there's the real-time stuff. These are the data that we have to update constantly as we're making ad decisions, because we need to retain that data to be able to get it back later on when the visitor returns so that we can do things like enforce the business rules about frequency or making sure that we retarget properly. That stuff is updated constantly. So we read that data at the start of a visitor session and hold it in memory during the session. So these particular servers are anything but stateless. We write data, as the data is being modified, we write it asynchronously. So that part isn't a blocker for us. We don't have so much concern for write performance, but we have a lot of concern for read performance, because when a visitor first hits the website, we don't want there to be much time between the time they are there and the page rendering time. You've got to make sure that the user experience is good for that page and that we're not taking too long to get their data activated. We have one SQL cluster for each of the AWS regions in which we operate, which is four different regions in different countries. So of course, we're co-located in the network with our decisioning systems. And we've got hundreds of millions of rows in each cluster. So for us, we wanted to encapsulate how we use NoSQL. So from our applications standpoint, we go through an internal API to access NoSQL. It's an abstract, object-oriented interface so that we can have multiple implementations. We've written that API to encapsulate our business-level function, such as get the selected rows for a single visitor. It is not CQL. And then we have an instance of a concrete class that we hold per tenant, per customer. We are a multi-tenant system. And we might have different instances of this NoSQL service object that we're holding for different tenants. We hold that behind a mutex so that we can change that on the fly, although it very seldom changes. It's only during times of migrations from one service to another where we would ever do this. But we hold it behind a mutex so that we can change it on the fly through configuration. So, don't panic, but here's a little bit of code. It's C++, and if you don't know C++, I think you can still make it out. It's not extremely tedious. But I'm showing two classes. One is an abstraction of the NoSQL service itself, and the main thing there is just to have an abstract method for getting a connection. And then we have an abstract connection through which we do all of our business logic. So we have a get function, get method, that would be given the timeout that we're going to use, who the customer is, what the ID of the visitor is, the data type that we're looking for, and then a reference to the data value to be returned. We return an integer for the status. And then we have one for get multiple, which is to get several different types of data for the same visitor, because sometimes we just need to get one type, and other times we need to get multiple types. And then we do updates and removes one type at a time. That's the business level at which we operate. So what implementations do we have? We have a memory-based implementation so that we don't actually need to have a real NoSQL database there for testing. We use that for our automated unit testing. We also have a flat file-based implementation that we use for testing on our local machines. Makes it easy so we don't have to worry about having a NoSQL cluster or even a virtual machine running on our local system to do something like that. And then we have our production implementations, which we started with in 2010 with Cassandra and Thrift, because all the cool kids were doing Cassandra back in 2010. And we stuck with that through 2014 using an open source Cassandra distribution. But our use of Cassandra was getting heavier. We wanted to have more support, so we switched to a DataStax distribution of Cassandra. And at that time, we switched over to using CQL. That was in 2015. We did that for a few years with that licensed distribution. And after having run for several years with this particular schema, I'll call it Schema A, we realized there were certain deficiencies in how we had constructed that schema, and we wanted to change it. So we came up with Schema B, which was better suited for the way we were reading and writing the data. But we wanted to implement it within the same cluster, so we did it with the same DataStax distribution and did that for the balance of 2018. And then our DataStax license was coming up for renewal, and we were looking at alternatives. I can't remember how Scylla came to us with this, but Scylla became something we investigated, and it offered the possibility. I mean, honestly, initially it was the attraction was we might save money, because we thought we might have smaller clusters. We thought we might have, the licensing itself was actually less expensive overall between the way they were pricing and the support that we've been getting from DataStax. It was looking favorable. And it offered the possibility, at least we were being told, that our performance might be improved. Although we were satisfied with the performance with the DataStax clusters. Our reads were running around 10 milliseconds, I think, on average. And under load, it was going higher, but it was okay. So being able to switch to Scylla involved no code changes whatsoever. I have to say this was one of the rare times in all the years that I've been doing software where vendors make promises about compatibility where it actually did not require us to make any code changes. We used exactly the same driver that we were using, the open source DataStax driver for C++, and we did not change any of that, and we did not change any of the SQL we were sending. But all of those transitions from one Cassandra to another Cassandra to Scylla to between schemas, those are all involving migrations, which of course you hear a theme around here. It's like every other presentation I attend here involves somebody doing a migration. Of course, the migration challenges can be where we need to change the schema within an existing cluster, where new NoSQL vendors are being used, as we have done twice now, switching to DataStax and then over to Scylla, or where your data needs to be transformed or moved. But how do you maintain that 24/7 access while you're doing the migration? Because we have to be able to continue to read the old data, and we have to be able to update the data as visitors are on the website. We have to be able to save this stuff back out. And we have to be able to finish the migration and decommission the old vendor, the old schema, in a reasonable amount of time. So here's what we did. We created a migrating implementation of our NoSQL interface. It wraps the two services that implement the old and the new schema, or vendor, depending on whether we were just doing a schema change or a vendor change. And so here's what that code does look like. The migrating NoSQL service itself doesn't really need to know anything about the old and new service other than just what's the reference to it. The migrating service in the constructor takes a reference to the old service. It takes a reference to the new service. When you ask it for a connection, it wraps the connections that it gets from those services to create a migrating connection. And then the migrating connection has the same methods as our API. So our application logic is totally oblivious about what's going on under the covers. All we have to do is switch a tenant over to using this migrating service. But how exactly do we engage those two services? We've done it 3 different ways, and I'm going to end with the third way, which is what we used with Scylla, which I found was the most effective. But the 3 ways we tried were lazy writing, lazy reading, and something I'll call aggressive lazy reading, which sounds like an oxymoron. So, lazy writing first. With the lazy writing, reads always delegate to just the old service, but writes delegate to both the old and the new services. So for instance, with the get method, we return just the old service's get, but with an update, we would do both an update with the old service and the new service. So the old service continues to be maintained with all the data, while the new service accumulates just the new and updated data. And then we decommission the old service after we deem that the new service has acquired enough data, which in our case was okay. If we let this run for 30 days or 60 days, the new service would accumulate whatever data was associated with all the visitors that were on the site during those 30 or 60 days. Oops. The advantages were it was simple. Disadvantages are that it sacrifices the data for the visitors who were not engaged during that migration period. And in order to give enough time to accumulate data for those visitors, you're prolonging the time that you're continuing to use the old service. Okay, so let's look at lazy reading instead. Lazy reading delegates to the new service first, reads, and if the no data is found, then it delegates to the old service. But writes only occur in the new service. So we don't bother updating the old service anymore. So here you see the get method asks the new service to do a get, and if the data value that's returned is empty, then we go to the old service and do a read. But when we do updates, we only update the new service. So, again, the old service is no longer updated at all. It's dormant, except for reads. Nothing's changing in the old service anymore, and all the new stuff is only going to the new service. And again, we have to decommission the old service only after the new service has acquired enough data. Its advantages and disadvantages are similar to the lazy writing. And it has the added disadvantage that it can require 2 reads. And in our situation, the reads are the more sensitive part. That's the part that's blocking when they first hit the page and we want to serve that first add to them. We have to get those reads done so we have that data in hand. And if we have to do 2 reads, and that makes the time a little longer. So, when we did the Scylla migration, we changed our strategy a bit, and we did this aggressive lazy reading, which is just like the lazy reading I mentioned, where it delegates to the new service first, and if no data is found, delegates to the old. Writing just goes to the new service. But we also then employ a separate script off to the side that walks the key space of the old service and copies all the rows over from the old service to the new service that don't already exist in the new service. Or, as we did as well, we had multiple of these scripts running in parallel, so they were all working on different slices of the data so we could get it done in less time. So there, the old service is no longer being updated at all, while the new service accumulates the new and updated data, and then we can decommission the old service after those scripts have finished. The advantages are we sacrifice no data whatsoever, and we migrate in less time, so the time to do the double reads is minimized. And the disadvantage, if you want to call this a disadvantage, you have to be really careful with that script. You don't want it to be running for a day or 2, and then it exits with an uncaught exception. So you've got to go do plenty of testing in order to make sure that you've got that script right. And it does increase the load on the new system while you're doing the migration. When we were doing testing on this initially, we ran, 75 or 100 of these things, threads in parallel doing this stuff, and we had a noticeable impact on our test cluster. So we had to back it off and have fewer threads, and we inserted some sleeps between reads just to kind of space it out a little bit. So our NoSQL Scylla migration We were in a real pinch because our DataStax license was going to expire in just a few weeks. And SAS, being a 14,000 person company, has enough of a bureaucracy in place with purchasing that the approval for the Scylla contract was dragging on, and we wound up getting to a point where we only had 2 weeks left between the time we had approval for Scylla and the time we were no longer going to be able to use DataStax. So, seeing that that was coming, prior to the Scylla approval, we were able to stand up test clusters, write the migrating script, the migrating service, and the script in Python using standard Cassandra drivers. And then after the Scylla approval, and I believe it was the same day, or maybe the next day, we started doing some testing of migration of data for test clients that were in our production cluster. So we stood up per cluster, we stood up a Scylla cluster, switched on the migrating service for, as I say, initially we did test tenants, and then we switched it on for all tenants so that at that point the old service, the DataStax cluster, was no longer being updated at all. We ran multiple copies of that one-off script in parallel to get the job done quicker, and when the script's finished, we were able to switch on the regular DataStax service for all the tenants. Because again, remember that we made no code changes, so we don't call it a Scylla NoSQL service. It's still called the DataStax NoSQL service because we're still using the DataStax driver. And then we tore down the DataStax cluster. So, the results. We completed the migration in just a few hours for the smallest cluster. And for the largest cluster, it took a couple of days. We finished all that. We did the clusters serially, since we could see that the time was not running so long. And we did them serially and completed them all within that 2-week window. We had no downtime. We lost no data. We didn't have any operational headaches at all. I mean, the ops guys, and this has been a continuing story with Scylla, is that it has been rock solid and has given us many fewer problems than we had with our Cassandra cluster. We had no customer complaints, and believe me, we would have gotten some complaints if we had not been able to activate user data that was needed to target ads properly. We would have heard about it from our customers, but they were oblivious. They did not even know we were doing this. And read performance improved because Scylla. The average read time, I believe now, is in the low single-digit milliseconds. And under load, the difference between Scylla and Cassandra is more striking. I mean, it does not get bad. So takeaway. Leverage the strengths of object-oriented design in your NoSQL applications by creating your own business-specific API that can lay the groundwork for you to be able to do good testing without actually having to have a NoSQL database, and gives you the ability to shift infrastructure more easily. Then implement concrete test classes for that testing, production classes for your real NoSQL instances as needed, provides some vendor independence, and can encapsulate a lot of the migration process.